Hey everyone, this video is about the Unit 6 review of Physics C Mechanics, which is called Energy and Momentum of Rotating Systems. Remember, I will be strictly following the AP course curriculum for Unit 6, so you will see things like uh, energy in the gravitation system of the satellite, gravitational potential, total mechanical energy, escape velocity, uh, then angular momentum, Kepler's law, conservation of angular momentum, omega, and all those stuff. Of course, you can download the link. You can download the worksheet from the link in the description. I think I have chapters, so you can also go to the respective question in case you're struggling with any particular one. And if you have any questions, feel free to post it down in the comment section. And if you need private tutoring, feel free to reach out. Okay, all right. The first question is on gravitation. It's a long one. It says that there are two systems. In the first system, there are two identical stars of m and radius r separated by d, and they are moving with a velocity of v1 in a circular orbit. Now the mass is doubled, but the radius is same, and now for the same distance d, they are moving with v2. So what is the ratio of v1 to v2? So the situation is something like this. This is the mass m, this is the mass m, and they are separated by a distance of d that is significantly larger than the radius. So we can disregard the radius, right? The distance between them can just be taken as d. Now, if we take the force on any one star, and remember, this is moving in a circle. Let's say I take the green force, which is given by capital G m1 m2 over r square, that is the gravitational force. And this should also be equal to same as the circular force, the centripetal force, which is m v square, which is v1 square over r. And remember, the radius will be half of d, so d over 2. Okay, let's equate these two and see what we get. So I will have gm square over d square will be equal to 2mv1 square over d. One of the d is gone, one of the m is gone, so it will be gm over d is equal to 2v1 square. Let's flip the omelette. So 2v1 square is equal to gm over d, which means that v1 is equal to root of gm over 2d. Now, the only change that they are doing in the second scenario is doubling the mass. So obviously, you might think, obviously, if you're thinking that you can just replace mass with 2m, that's absolutely correct, because doubling the mass will just only change this while the distance remains the same. So v2 will become g times, and a factor of 2m will come over here over 2d square root. And isn't that very clear? What is the ratio of v1 and v1 is to v2 from here? Isn't that just 1 is to root 2? Because v1 over v2 is root g m over 2d divided by square root of 2gm over 2d. So this will be square root of gm over 2d multiplied by square root of 2d over 2gm. These two are gone, these two are gone. I'm just left with 1 here and over root 2. Okay, but they need the value of v2 is to v1. So v2 is to v1 will obviously be exactly opposite. So v2 is to v1 is square root 2 over 1, which should be option D. There you go. That's the correct choice. Right. The next question is, an asteroid is heading straight for Earth. The asteroid has this much speed, and relative to the center of the Earth, when it is at a distance of this many meters from the Earth's center. With what speed does the asteroid hit the Earth? Assume that the Earth is the only body exerting gravitational force. Ignore any resistance from the Earth's atmosphere. So this is more about the energy conservation of the system. The radius of the Earth is given to us, by the way. This is a part of the question. So at this point, we have two scenarios. That at this point we have speed of the asteroid, which is given to us. Let's call it v, and there's a distance given to us. And then at this point, it hits the Earth. Let's call the speed as v2, and let's say this is v1. So at point A and at point B, we are going to conserve the energy. At point A, the energy is going to be half mv square, and mass of the asteroid we do not know, and we don't even need that. So half times m times v1 square. And at this point, the potential energy between of the system of the asteroid and Earth, this is a system, so it will have a gravitational potential energy which is negative g m of asteroid mass of Earth divided by the distance between them. The distance between them is what do you call it as, it's given in the question already, which is this 3.84 times 10 to the 8. And finally it will have half m v2 square that we do not know, and minus g m mass of the Earth over 6,400 kilometer, which can be written as 6,400 times 1,000, and that should obviously be when I convert everything in meters. So we don't need the mass of the asteroid because m is gone from all the sides, and now I'm just supposed to plug in the numbers. Obviously, this is going to be a little gross, but we will use Desmos. I'll just plug in all the numbers here so that you understand where will be what. So this is V1. G is, let me put the G in a minute. Let's write it as it is GME over 3.84 times 10 to the 8. Add that thing on both the sides. So adding this on both the sides will be GME over 64 times 10 to the 5 is equal to half V2 square. Okay, now this thing can obviously be taken as a factor, so I'm left, and we can multiply 2 both the sides as well. So when we multiply 2, then 2 times 1 half is gone, so I'm just left with 14.8 times 10 to the 3 square minus GME, and this will be 1 over 3.84 times 10 to the 8 minus 1 over 64 times 10 to the 5 is equal to V2 square. Yes, mass of the Earth will also be a part of the question, which is 6 times 10 to the 24 kilograms. So don't worry, that is a part of the question. You can use it. And let's plug in everything in Desmos. And yeah, sorry, I forgot there should be a 2 over here because we multiplied 2 both the sides. So don't forget that this is a 2. Now let me just share the Desmos. Okay, so there you go. I plugged in everything for you. You can have a look at it. Just the first, velocity square minus 2 times g value, which is right over here. This is the g value, and then this is the mass of the Earth. This is the other entities, and the entire thing is in the square root. So I'm getting somewhere around 18,493. And yes, I think 18,493 matches perfectly with 1.85 times 10 to the 4, which is 18,500 around, which of course is the approximate value. So the velocity is somewhere around 1.85 times 10 to the 4 meter per second. That's the answer. Right. The next question is the Earth mass is given, has a radius of this. Suppose your friend wanted to throw a 145-gram baseball battle to the ground from a hot air balloon 20,000 meter above sea level. Neglecting air resistance and height changes of the landscape, at what speed would the baseball need to have after your friend throws it to enter the free fall orbit and never fall to the ground? This is just really a fancy way of saying that what is the orbital velocity of the baseball, because if it enters the free fall orbit and never falls to the ground, don't think that this is the escape velocity. Escape velocity, had this was escape velocity, then enter in the free fall orbit will not make sense. Entering in the free fall orbit means it just keeps circling around. And what is the formula for the orbital speed? That's just square root of g me over r, because in this case we have Earth. So all we need to do is plug in g as 6.67 times 10 to the negative 11. Mass of the Earth is given to us in this case is 5.972 times 10 to the 24. Just be careful with r, because the baseball is somewhere over here above the sea level, and we have to take, this is obviously 20,000 meters, and we have to take the radius of Earth into account as well, because the distance is always calculated from the center of the Earth. Radius of the Earth is 6,371 kilometer. So it will be 6371000 plus 20,000. And if we find this, this comes at somewhere around 7,897 meter per second. So this will be the orbital velocity, which is option C. All right, next question is, consider two satellites both in circular orbit around a very heavy planet. Satellite 1 has a mass of m, radius r. Satellite 2 has a mass of 3m, radius of 2r. What is the ratio of kinetic energy? The formula for kinetic energy of a satellite is given by g m of satellite, m of the planet over 2 times r. If you write KE1, that will be G times M. Actually, this is just KE1 because that's just, no funky stuff. But for kinetic energy 2, the mass of the satellite is 3m, planet is not changed, and its radius of the orbit is 2r. So it will be, the r is replaced by 2r. Remember, this 2 is a part of the formula, right? Okay, so this will become what? 3 GMMP over 4R. And now we just have to take the ratio of this. So KE1 divided by KE2 can be written as GMMP over 2R divided by 3GMMP over 4R. Keep change flip. So GMMP over 2R times 4R over 3GMMP. GMMP, R and R is gone. So I'm left with 4 over 6, which is 2 over 3, which should be option C. Okay, in this one, they are literally just trying to confuse us. The question says that two identical small moons are traveling in elliptical orbits around a planet of mass capital M. They crash into each other and stick together, then settle into a stable circular orbit of radius r. If the moons originally have a mass of m, then what is the orbital speed of the new circular orbit? Remember that the orbital speed does not depend on the object that is rotating, but on the planet. So since the formula is root gm over r and mass of the planet is not really changing, radius of the planet is just same as r, you might think that it is E because the two masses, join and becomes 2m, but no, it does not depend on the mass of the object that is rotating, but on that planet, so which is just capital M. So the answer is option A. All right. This one is, a planet with a mass of m was moving in elliptical orbit. The radii of point A and B are Ra and 3Ra. And the kinetic energy of the point at A is Ka. Then what is the planet's orbital speed at B in terms of Kam and universal constants? So first we need to use the conservation of angular momentum to find the respective speeds. Let's say the speed at A is VA and the speed at B is VB. As you can see that the angle between the velocity vector and the radius vector in both the cases is 90 degree. So when we conserve the angular momentum, I'm going to say that M VA RA sine of 90 is equal to M VB RB sine of 90. M and M is gone. VA I do not know. RA is just RA. Sine 90 is 1. VB is unknown. RB is 3 times RA given in the question, and sine 90 is 1. Okay, so this means that RA and RA is gone. So if we flip the omelette, then 3VB is equal to VA, and VB is equal to VA over 3. That's the velocity at B. Now, what is the kinetic energy then? Kinetic energy at B is going to be half m. Sorry, they are looking for orbital speed. Never mind. They are looking for orbital speed. So we need to convert or rewrite VA in terms of kinetic energy. We can do that because kinetic energy at A is half m VA square. So 2Ka is equal to mVA square. So 2Ka over m is VA square. So from here, I'm going to sub in the value of VA over here. So VB will be equal to 1/3 of VA, which we get by taking square root on both the sides. So square root of 3 KA, I'm sorry, it's not 3, it's 2, it's 2 KA over M. So this is finally going to look like square root of 2 over 9, because uh, this 9, if you take out, it is just 3, or if you bring this 3 inside, it will become 9, because I need to match the options. It will be square root of 2 Ka over 9m. That's another way to write the same thing, which is option C, right? I hope you understand. I mean, if you take this 9 out from square root, you have 3, right? So option C can be written as 2 Ka over m square root with 1 over 3 on the outside, which is right here, option C. Yeah. Right, that was a pretty decent one. A satellite is circular in circular orbit, has a radius r and orbital period of tr. If the satellite is now moved to a new circular orbit with a radius of 4r, what is the ratio of the new time period to the original? So Kepler's third law will be really helpful here, which states that t square is proportional to r cube, which means that tr square over t4r square will be equal to, because when we divide them, the proportionality will be gone. It will just turn into an equal to, is r cube over 4r cube. So tr square over t4r square will be r cube over 64r cube. These two are gone. So I'm left with tr square over t4r square is 1 over 64. I'm just going to take square root on both the sides. So tr over t4r will be 1 over 8, which means that 8 times tr is t4r using cross multiplication. So you can see that they are asking what is the ratio of new period to the original. So let's just, I mean, I could have just flipped the omelet over here, take the reciprocal on both the sides. So t of 4r over t of r will just be 8 over 1. That looks like option D. All right. What is the mechanical energy of a satellite of mass m in circular orbit r around a planet of mass m? This is a really straightforward question. This literally just formula based. So the mechanical energy, I will write all the three energies. Kinetic energy is given by g m capital M over 2r. M is the mass of the satellite and M is the mass of capital M is the mass of the planet. Potential energy is negative g m capital M over r, and total kinetic energy or mechanical energy, when we add these two, is negative gm capital M over 2r, which is option B. That should be the answer. Okay, a satellite is launched from the surface of the moon with an initial velocity of magnitude v0. Which of the following are conserved by the satellite moon system throughout the orbit? Okay, this is more factual, because whenever a satellite moves around a planet, its mechanical energy is always conserved. We just saw its formula above. So mechanical energy is always conserved. Linear momentum is never conserved, but the angular momentum once again is conserved, because I think in question 7 we just did that, right? Or maybe question 6. Yeah, there you go. This mvr sine theta is nothing but angular momentum. So angular momentum is always conserved. So uh, these are facts, and 1 and 3, which means that I should mark option D as my correct choice. That should be the correct answer. Yeah. Okay. Consider this kilogram planet with this radius. At what speed would a projectile being shot vertically from the surface of the planet need to be going to escape the gravitational pull of the planet? This is a fancy way of asking what is the escape velocity. So escape velocity is given by root 2 gm over r. So that will be square root of 2. G is 6.67 times 10 to the negative 11. Mass of the planet is this, which is 3.109 times 10 to the 30 over the radius of the situation of that projectile, which is 5.15 times 10 raised to 10. Let's plug that in. So I'm going to get 89739.7 meter per second, which is closest option is 90,000, because this is somewhere around 89.7 kilometer per second, which, yeah, matches with option C. All right. Here we are given that two satellites X and Y of equal mass m and equal size. Okay, so their radius is same, are in circular orbit around a planet of mass m and radius r. Okay, fair enough. Initially, X is orbiting m at an orbital radius 3r. I can see that, and the other one is at 4r. The initial kinetic energy of X is Ka. Then an external force P moves satellite X to the same orbit as Y, such that X now has the same circular orbit as Y. In terms of X's initial kinetic energy, how much work is done by force P in moving X to its new orbit? Okay, so as the work done is basically the change of mechanical energy, right? So I need to find the total mechanical energy here, total mechanical energy here, and subtract. The only well catch is that should be in terms of kinetic energy. So that's where the relationship between the energies come into picture. Remember that the kinetic energy is always same, equal, and opposite in sign to the mechanical energy. And just so you know, these guys are also equal to negative of negative of potential energy divided by 2. This is the relationship that we get from the three formulas that I wrote earlier. If you find a relationship, it will be this, and this is pretty important. So we just need the first two, that kinetic energy, mechanical energy is just the opposite of the kinetic energy. So at this point, the kinetic energy is already given as kx. The kinetic energy at x formula, that is going to be g m capital M over 2 times the r, which is 3r. So this comes out as g m capital M over 6r, or multiplying by 6 both the sides. 6kx is equal to g m capital M over r. Likewise, ky will be g m capital M over 2 times 4r. 4 times 2 is 8, multiply 8 both the sides, so 8ky is equal to gm capital M over r. Why I did all that is because I want ky in terms of kx. Now look at gmm over r. Isn't that same as 6kx? So that's what I'm going to plug in over here. 8ky is equal to 6kx. So ky is equal to 6 over 8kx, or 3 over 4 kx. And now all I need to do is subtract the mechanical energy. So it will be mechanical energy at y minus mechanical energy at x. That's going to be the work done. Mechanical energy is negative of kinetic, so negative of ky minus negative of kx. So it will be negative ky plus kx. So kx minus ky. So kx minus, and ky is 3/4 of kx. So this will become 1/4. 1/4 of kx positive. That is the work done, which is option E. That should be the correct choice. Okay, two planets C and D are orbiting around the same star. The planets have equal mass and they both are in circular orbit. Planet C has a smaller orbital radius than D. Then which of the following is true? And the options are about energy. Okay, just to write the formulas once again. In fact, I don't really need to write all the formulas. I know that kinetic energy is inversely proportional to R, and potential energy is inversely proportional to negative 1 over R, and total mechanical energy is also inversely proportional to negative 1 over R. So if planet C has a smaller orbital radius, obviously this denominator is small, which means that its kinetic energy will be more. So that is for sure that the kinetic energy of planet C is more. So planet C has more kinetic energy, which is definitely going to uh, be over here. And unfortunately, three options are adding up with that. But since this is a negative reciprocal, so because of negative reciprocal, if you increase the value of r, this value will, decrease the value of r. This value will increase in the negative direction. You understand what I mean? For example, this one was 2 joules, so this now became 8 joules. But this one was initially negative 2 and became negative 8. And sort of like negative 3 became negative, I don't know, 9. So these values actually decrease, right? Decrease. So they have less potential as and less mechanical energy as compared to D. So option A should be the best choice. I hope this makes sense. Okay. For an elliptical orbit sketched at right, which of the following statements true about A and B? The mechanical energy and the angular momentum are greater. So this is for sure. We just learned that mechanical and angular momentum are always conserved, right? So mechanical energy greater at point A and B doesn't make any sense. This also doesn't make any sense. Is there any option that is saying that, yeah, should be C, right? Mechanical energy of the system and the angular momentum of the satellite around the planets are the same at points A and B. Obviously, Kepler's law and the mechanical energy thing, that's a fact. Okay, when two masses separated by a distance r are brought closer, ending with a separation of r over 2, the gravitational potential energy of the system. So this is again the same thing, right? Gravitational potential energy of the system is inversely proportional to r. So when the distance becomes half, or sorry, negative 1 over r, right? So if the distance becomes half, this will become a factor of negative 2 because it's inversely proportional to r. So initially, if it was negative 2 joules, now it will become negative 4 joules because half radius means it will become double in magnitude, but remember the sign will be as well. So what happens with this? This increases by a factor of 2 or decreases? I mean, it increases, it decreases, right? Decreases by a factor of 2. It should be option C. Okay, that was pretty straightforward. Satellite is placed in circular orbit of radius r, and second satellite is placed in circular orbit of 2r. Compared with the first satellite, the second will have less energy and less angular momentum. Okay, so this is about the total energy first off. So total mechanical energy is inversely proportional to the negative of radius. So if the distance is more, this number will become less but with a negative sign. For example, initially it was negative 2 joules, now it will become negative 1 joule. So obviously energy will be more. So less energy is gone. It should be more energy. And angular momentum is given by mvr sine theta, right? Theta is 90 because these are circular orbits, so mvr. Now, remember that the mass is compared to the first satellite, their mass is same, although it's not given in the question, but a second satellite, that satellite is identical. So you have to take the same mass over here. So M1, V1, sorry, MV1, R1. Now we need to eliminate this V because we know that the orbital speed is given by root of gm over r1. R1, so this will become m root gm, and r over root r will become root r. So this means that angular momentum L is proportional to root r. So more is the radius, more is the angular momentum. So for a second orbit, the angular momentum will be more. So compared to the first, the second will have more angular momentum. It should be option D. I hope this makes sense. All right. Over here, satellite S is in an elliptical orbit around the planet M with a radius of R1. R2 being its closest and farthest, R1 and R2 being its closest and farthest distance respectively. What is the speed at the farthest distance if the closest one has V1? This is again a conservation of angular momentum. So I'm going to say M V1 R1 sine 90 because this is 90 is equal to m v2 r2 sine 90 once again. So M is gone. V1 R1 is equal to V2 R2. Flip the omelette. So V2 R2 is equal to V1 R1, which means that V2 is V1 times R1 over R2. Pretty straightforward, which should be A, I think. Yeah, A should be correct. Okay. Escape velocity for a rocket at Earth's surface is VE. What would be the rocket's escape from a surface of a planet with twice Earth's mass and the same radius? So escape velocity is given by square root of gm over r. Sorry, 2gm over r. And they are saying that the mass is doubled over here, right? The radius remains the same. So if the mass is doubled, obviously this double means that a square root 2 factor, I mean, I can definitely do that for you. VE, let's call it dash, will be square root of 2g 2m over r, which will become square root of 4gm over r. We need to find the ratio. So VE dash divided by VE is going to be square root of 4gm over r divided by root 2gm over r, which will be square root of 4 g. Square root of 4 is 2, so 2 root gm over r times square root of r over 2gm. The square root can be taken out, so it will be 2 root gm over r times 1 over root 2 square root of r over gm. Square root of r gone, gm square root gone. So I'm left with 2 over square root of 2, which is square root of 2. So this means that a VE dash over VE is square root of 2. This means that VE dash is square root of 2 times VE, which is option B. Yeah, option B should be the correct choice. Okay, the figure above represents, I mean, the below figure represents S2 and S3 of equal mass orbiting Earth in circular radii, da da da. What is the relationship between kinetic energy and angular momentum of S3 compared to S2? We just proved a similar question for angular momentum, and we learned that more is the radius, more is the angular momentum. So this is for sure that the angular momentum of S3 is greater. So it has to be either option A or B. And kinetic energy is inversely proportional to positive 1 over r. So more is the r, less is the kinetic energy. So kinetic energy is less for S3 and angular momentum is greater for S3. I hope this one makes sense because we already did most of the work earlier, right? So yeah, this is how we do it. Okay. Okay, this time they're asking for the graph. An object moves away from the surface of the Earth. The graph of gravitational potential energy is. Uh, what is the formula for gravitational potential energy? Isn't that just inversely? I mean, obviously the exact formula is negative g m m over r is inversely proportional to negative 1 over r, remember. Had this was positive 1 over r, it would have looked like this, but since this is a negative outside, it will be in quadrant 4, and it will be obviously this is called rectangular hyperbola, so it has to be option A. It's a pretty straightforward, more math than physics, but yeah, that's how it is option A. Okay, there is a total mechanical energy of a satellite M orbiting Earth at a distance equal to 2 times the Earth's radius above its surface. Be very careful. 2 times Earth's radius above the surface, right? Above the surface would mean that this guy is 2 times RE and this is already RE. So remember that be careful, the total distance will be 3 RE. So the total mechanical energy formula was negative G M M over 2R. So all we have to do is negative G M M over 2 times R will be 3 RE. So it will be negative G M M over 6 RE. That will be the total mechanical energy, which looks like, isn't that just option A? Yeah, it should be option A. Right, the radius of Earth is r and acceleration due to gravity is g. If a body of m is sent to a height of r over 4 from the Earth's surface, the potential energy increases by. So the formula for the potential energy is given by negative g m m over r. At the surface in situation A, it is just negative g m m over capital R. And in situation B, it is r over 4 from the Earth's surface. This means that its total distance from the center will be r plus r over 4, which is 5r over 4. So this will be negative gmm over 5r over 4, which is just negative 4/5 of gmm over r. That is the potential energy at B. So potential energy at A is here, at B is here. We are looking for a change. So the change is going to be potential energy at B minus potential energy at A, which is negative 4/5 gmm over r minus of minus gmm over r, which is negative 4/5 of gmm over r plus gmm over r. 1 minus 1 over 4 over 5 is just 1 over 5, so it's 1 over 5 gmm over r. Of course, not in the options because they need in terms of acceleration due to gravity. The formula for g was gm over r square, which means that if I multiply both sides by r square, I get the g capital M value. So let's replace that g capital M over here. First, I'm going to rewrite it as 1 over 5th small m over r gm. And this gm is now replaced by g r square. One of the r, of course, is gone, so I'm left with m g r over 5. So that should be the final change, which is, yes, indeed, option C. Yeah, makes sense. This could have been done in another way as well using mgh and all. But yeah, I just wanted to use the potential energy formula so that you will get, some practice as and how to apply these things. Right, satellite in the circular orbit of radius r has this as E. Total energy, we know that. What minimum work must an engineer deliver to send it to infinity? Okay, so there are two things. Infinity means the potential energy at that point is zero, and minimum means I want the kinetic energy at that point also to be zero. So in other words, at A, the mechanical energy is given by negative g m m over 2r, and at B, both are zero. So the work by the agent is mechanical energy at B minus mechanical energy at A. So it is 0 minus g m m over 2r, which is g m m over 2r. So that should be the work. That's straightforward. It should be option B. That's what we have. Guys, if you're liking this video so far, please like and subscribe. Please share it with your friends. And if you need private tutoring, feel free to reach out. A wheel with a known moment of rotation inertia I is mounted at rest on a fixed axis through its center. In order for the wheel to rotate, a constant torque is applied to the wheel. Which of the following quantities would be most helpful in determining the energy added to the wheel while this torque is applied? I think that's pretty straightforward because if we want to know the energy, then the energy due to a torque is given by tau times the rotation, the angular displacement, that is theta, if the torque is constant, which it is in our case. So we need theta or the number of rotations, because from number of rotations I can figure out the angular displacement as well, if it makes sense. Right, guys, so jumping into the territory of angular momentum now. A marble of mass m is moving at the speed of v towards another ball of mass m attached to the point P by a light rod. Marbles stick together. What is their angular speed immediately after the collision? Um, I am going to conserve the angular momentum here, because whenever the net torque is zero of the system, so I'm going to conserve the angular momentum in this case. If you're thinking that why is the linear momentum not conserved, because this guy is is a rod, right? It is exerting, as soon as it collides, it exerts an external force on the system. So linear momentum is not conserved. So we are going to conserve angular momentum. The initial angular momentum is only because of this mass, and this is the angle that we are looking for. I hope you remember the formula for the linear momentum, a special formula for the point mass. It is mvr sine theta, where r is the distance between that point and the pivot, theta is the angle between the velocity and the r, and then v is just v. Obviously, we don't know theta, and obviously we don't know r, and that's why I made this triangle, so that I can say that sine theta is opposite over hypotenuse. So r sine theta is just L. And this r sine theta I'm just going to replace by L, which is mvl. That is L initial. And L final, remember that they stick together. So this is 2m, and they have some omega, and this is L. So I think it is worth, it would be fair to use I omega as the formula now for the final angular momentum, where I is m r square and r is L, because these are, we are not given any radius, so we are just going to assume these are point masses times omega. And these two guys should be equal because the angular momentum is conserved. So 2ml square omega should be equal to mvl. M and m is gone, one of the L is also gone, so 2L omega should be equal to V, which means that omega should be equal to V over 2L. That is the angular speed immediately after the collision. So it should be option C. Guys, if you have done linear momentum conservation, I think you will again get C, but remember, it's just a happy coincidence, but linear momentum is not conserved. That is not a legitimate physics that you will be doing. So angular momentum is conserved. Linear is not conserved. Just be advised here. Okay. A ring of mass m radius r is released from rest on an incline from height h. The ring rolls without slipping. At the bottom, what is the angular momentum of the ring about the center? So in other words, I need to find omega. And for omega, I need to conserve the energy. So let's say there is some velocity v and some omega at the bottom. Uh, the initial energy is just mgh, because this is the height over here, and the final energy is half mv square plus half I omega square. We are not given any I over here, right? So I think they want us to, or probably let's just keep I as I. So this will be mgh. Actually, you know what? This is a ring, so I'm just going to replace by mr square. I think this is going to make my life a little easy. And v is omega r, so omega r square plus half mr square omega square. Yeah. Okay. M is gone, so I'm left with gh is equal to half omega square r square plus half omega square r square, which is just omega square r square is equal to gh, which means that let's flip the omelet. So omega square r square is equal to gh, which means that omega square is gh over r square, which means that omega is root gh over r. And now we need to find the angular momentum, which is I omega. I is, for the ring, is mr square, and omega is root gh over r. One of the r is cancelled, so I'm left with mr root gh. Oh my goodness, that's a gross expression. I hope that is in the options. Yes, indeed, option A. That should be the correct answer. Okay. Particle of mass m moving with v, magnitude angular momentum about the. This is the honestly the same type of question that we did, because its radius is given as, this is d over here that we are given already, and we need to figure out what this theta is, right? What this theta is. So the angular momentum is going to be mvr sine theta. M is M, V is V. We need to find the angular momentum about the origin. So R is D. And theta, if we notice carefully this triangle, uh, uh, this tan theta will be opposite over adjacent, which is d over d. So tan theta is 1, or if you are honestly, I'll just do sine theta, guys, if you might be confused. So if this is d, then this will be square root 2d, and sine theta will be opposite over hypotenuse. So that's going to be 1 over square root of 2, that is sine theta. I'm just going to plug that in over here. So that's just 1 over square root of 2. So that will be mvd over square root of 2, which looks like option C. That should be the best choice. Right, guys, I hope this one makes sense. Okay. Uh, 5 Newton meter torque acts on a thin hoop with a mass this and a radius this for 10 seconds. If the hoop starts from rest, what is the new angular velocity? The moment of inertia is given. Isn't that pretty straightforward, guys? We need to find alpha, of course, which is torque over I, because, torque is equal to I alpha. Torque is 5 Newton meter. I is, we don't know, but we are given the formula, which is mr square. M is the mass, which is 0.5. R is 0.15 square. So this guy comes out as 0.01125. If we put that I over here, 0.01125, then alpha comes out as 444.44 radian per second square. I am interested in the angular velocity, final angular velocity. So omega final is equal to omega initial plus alpha t. Omega initial is 0 because it starts from rest. Alpha we just found, it's 444.44, and the time is 10 seconds over here. So the answer will be 4444.44 radian per second. Well, that's a lot of force. And yes, the answer is also option 4, or option D, which is 4444 radian per second. Okay. What's going on here? A particle with a mass of 12 meter per second. Yes, I can see it at 30 degree, over here. Okay, above the horizontal. So this guy is 30 degrees over here. A line is drawn from P to the particle. From P to the particle is 3.5 meters long and makes an angle 55 degree. Okay, so this is 3.5 and this is 50 degrees, sorry. What is the angular momentum of the particle with respect to the point P over here? So this is the velocity. We are already given this r over here, so I'm just going to disregard this 3.5 because this has no relevance. So I'm going to say that the momentum of the angular momentum is obviously mvr sine theta. M is 1 kilogram. That's written over here. Teeny tiny guy. Velocity is, there you go. That's my boy, 12. R is, of course, about point P. That's 3.5. So that's 3.5. Now, theta is, be careful, this entire thing. And if this is 50, then these are alternate angles. So this should also be 50. So the total angle that we are looking at is, yes, it is indeed 80 degrees. So let's multiply all these people up. So I am getting 41.36 kilogram meter square per second. So I think the best choice should be option not E. It should be D. Yeah, that guy is the closest guy. I think that's what I'm gonna go with. So that should be the answer over here. All right, fellas. This question is this is spherical star of radius r that is spinning with omega. As part of its life cycle, the star collapses to a smaller diameter while maintaining the same mass. What is the new angular speed when the okay, this is a classic question of conservation of angular momentum because it's spinning and net torque is 0, and so I'm gonna say that L initial is equal to L final. So I1 omega 1 should be equal to I2 omega 2. Okay. Moment of inertia is given by, since this is a spherical star, so I'm going to say it's 2/5 mr square. So 2/5 mr square times omega initial is just omega. And final I is 2/5 mass remains same, and the radius is just half. So r over 2 square, and omega 2 I do not know. So 2 fifth m is gone. So r square omega is equal to r square over 4 omega 2. R square is gone. So multiplying both sides by 4, we have 4 omega is equal to omega 2, or omega 2 is 4 omega over here. So omega 2 is 4 omega. That is our answer, which is option B. Right. For a solid cylinder of mass and radius are rotating at omega, when a non-rotating hoop of equal mass and radius drops onto a cylinder. In terms of initial omega, what is the new angular velocity? And the moment of inertia of cylinder is this, and of hoop is this. Again, a very classic question of the conservation of angular momentum, because when this disk is rotating, and when this hoop is placed on the top of it while this was at rest, this hoop will try to slow this cylinder down, and this cylinder will try to speed the hoop up. And whatever the torque is involved between these guys, that is equal and opposite, and as a system it cancels each other, and then they will start moving with a common omega. So initially the angular momentum is only because of the cylinder, which is I omega. I is 1 half mr square, because it's given in the question that the moment of inertia of the cylinder is half mr square, times omega. M and R are small, so that's fine. I can just replace with the small case, although it doesn't really matter. Finally, their moment of inertia will be I hoop plus I cylinder times omega. I hoop is, remember, it's mr square, and the mass and the radius is same. So I'm just going to write mr square here, and cylinder is half mr square, and that should be omega. So this should be 2 over 2, 3 over 2 over here, 3 over 2 mr square omega, and all we need to do is set these guys equal. So I'm going to say that 3 over, I think omega and omega is overlapping, so let's call this as omega dash. So I'm going to say that 3 over 2 mr square omega dash, or omega prime if you have the feel of calculus, is 1 half mr square omega. Half gone, mr square gone, so we are left with 3 omega dash is omega, which means that omega dash is just omega over 3, which looks like option A. That should be the correct choice. Okay. A solid cylinder of mass and radius r, when rotating at an angular velocity, has a momentum, angular momentum L. Which of the following will double the angular momentum? So let's first write the formula for the angular momentum. It's just I omega. I of a solid cylinder is 1 half mr square, and omega is just omega over here. So that is the value of L. Now I want to double the angular momentum, right? So let's read the options. Doubling the mass of the cylinder while halving is angular velocity. I don't think so, because if I double the mass and if I halve the angular velocity, then these two effects will nullify each other, because this will be a 2 and this will be a 1 over 2, which will cancel. So omega L will not change. Doubling the angular velocity while halving the mass, once again, I again no, because if you double the angular velocity and half the mass, again the same situation is going to happen, that it is going to nullify. Doubling the radius while halving the mass of the cylinder, I think that could work, because doubling the radius would make it a factor of 4, because that's 2 square, right? So there will be a factor of 4, and the mass of the cylinder should be half, so there should be a 1 over 2 over here. So 4 over 2 is just 2, and yes, that's what I want. It should be doubled, so it should be option C. The others are not going to work. You can definitely check those options, but yeah, it should be option C. Okay. The next one is there is a ball of mass m that is released from rest at position A. after falling from a height of h, what is the magnitude of the angular momentum of the block about point C when it reaches B? So it's pretty straightforward. I think all I need to do is find its velocity, because at this point I will have the angular velocity as just mvr sine theta. M is just m, v I need to find. R is obviously this distance. Oh, I also have to find this, which should not be a problem because that's just a trigonometry. And theta is just 90 degrees. So that's just 90 degree over here. So it will be mvr. Okay, let's find both these one by one. For velocity, I think I can use kinematics. So v final is equal to v initial plus at. It's released, rest, so 0. Acceleration is just g and time is just t over here. But we don't know the time, right? Oops, wrong equation. I think we need to use the third equation because we know the displacement. So v final square is equal to v initial square plus 2as. So 0 square plus 2 times g times h. So it is root 2gh. That is the v final. You could have used energy conservation as well. And for R, I'm going to, of course, pay attention to this triangle. I'm interested in finding R, so I think cosine will help me. Cosine theta is adjacent over hypotenuse. So L cos theta is R. That's about it. Let's plug all these guys in. So m times velocity is root 2gh times r is L cos theta. So the answer is m L cos theta root 2gh, which is ml cos theta root 2gh is sorry guys, there is a typo in the question because if you notice B and C are same. This guy is cosine theta, so it should be option B. So ml cos theta times root 2gh. All right. For this one, there is a solid cylinder of mass m and radius r rotating at omega. When a non-rotating cylinder of double the mass and equal radius drops onto the cylinder. By what factor does this change the rotational kinetic energy with regard to its initial rotational kinetic energy? So this involves energy, but to start with, we need to conserve the angular momentum. Okay. Angular momentum of the cylinder is given by 1 half mr square. So that's for cylinder number 1. And for cylinder number 2, it is double the mass given over here. So 2m and equal radius. So that's just mr square. So initial angular momentum is given by I omega. I is half mr square and omega is just omega. And final angular momentum is given by I omega, but I should be for both, right? Because they both are moving together now. So half mr square plus mr square and then omega, let's call it omega dash, that we do not know. So this will become 3 over 2 mr square omega dash, that is the L final. Obviously, these two guys should be equals because the angular momentum is conserved. So I'm going to say that L final will be equal to L initial. L final will be equal to 3 over 2 mr square omega dash will be equal to 1 half mr square omega. 2 gone, m gone, r square gone. So what are we looking at here? 3 omega dash is equal to omega, which means that omega dash is omega over 3. But they are interested to know that by what factor does this change the rotational kinetic energy with regard to its initial rotational kinetic energy. So initial energy is I omega square, of course, I omega square. Now we need to convert the kinetic energy. So initial kinetic energy is I omega square over 2, which is going to look like 1 over 2 times I, and I is 1 half mr square times omega square, which is 1/4 mr square omega square. That is the initial kinetic energy, right? The final kinetic energy is, I think I'm going to run out of space. So, okay, I'm still going to try it. is I nu omega square over 2, right? So 1 half I nu is, there you go, sitting right here, 3 over 2 mr square. So 3 over 2 mr square and omega dash square, and omega dash is omega over 3. So mr square and omega over 3 square. So 3 square is 9 and 3 is over here. So 3 over 4 times 1 over 9 times mr square. 3 over 9 is 1 over 3. 4 times 3 is 12. So it's 1 over 12 mr square. This is the K final. And all we need to do is now take the ratio of these two. So K final over K will be equal to 1 over 12 mr square omega. I think I left an omega square here. There should be an omega square, guys. Let me fix that. Okay, so half m r square omega square over the K, which is 1/4 m r square omega square. So keep change flip, it will become 1 over 12 times 4 over 1, and 4 over 12 is 1 over 3. So this should be option B. I think B makes perfect sense. It was a pretty good question, right? Again, guys, if you're liking this video so far, please like and subscribe. Please share it with your friends. And if you need private tutoring, feel free to reach out. Particle of mass m moving in a circle with radius r and constant alpha. After one revolution, what is the angular momentum of the particle around the center of the circle? So I know that at any point, the velocity is always making a 90-degree with the center, because this is the tangential velocity. So it has to be mvr because sine 90 is 1, right? So that's what we are looking at. M is just m and r is just r. We need to figure out what v is, and for that I need to take the alpha into consideration. One revolution would mean a theta of 2 pi. So I think I can use the omega final square is equal to omega initial square plus 2 alpha theta. Starts from rest, alpha is alpha, theta is 2 pi. So omega final square comes out as 4 pi alpha. And if you're going to take a square root of this guy, so omega final will be equal to root of 4 pi alpha. I'm looking for V, and of course V is related with omega as well, because V is equal to omega R. So I'm going to replace that with omega R. So it will look like m r square, and omega is root 4 pi alpha. And what is square root of 4? 2. So that 2 comes out, 2 mr square root pi alpha. There is a slight typo in the options. It has to be option E, and this is 2 pi r square root of pi alpha. So option E matches with the answer. And then we have planet Xenon has twice the mass of the Earth and orbits its star at the same orbital distance that the Earth orbits the Sun. If the planet takes 365 and a quarter days to complete one orbit, then how does the angular momentum of planet Xenon compare to the angular momentum of the Earth, assuming both are orbital? This is based on Kepler's law, guys, Kepler's second law, where angular momentum of Xenon and angular momentum of Earth is conserved. Angular momentum is mvr, so m1 v1 r1. I'm skipping sine theta because that's just going to be sine 90, as they are circular in nature, so tangential and centripetal kind of stuff. So this is equal to m2 v2 r2 over here. They are asking to conserve angular momentum. So why am I even doing all this? Isn't the answer just option E, because their angular momentum should be equal? Right, let's talk about the last question that we have here. Rod is initially hanging straight down from a pivot point at the top, A piece of clay that is initially moving horizontally strikes the rod and sticks to it. Which quantities are conserved during the collision? Once again, this is only a conservation of angular momentum and not linear momentum. I think we have done a similar question, uh, you know, earlier, and the idea is that this rod is applying a force, external force, because of which the angular momentum is sorry, the linear momentum is not conserved. And since it sticks to it, there is no point of conserving the kinetic energy as well, because we know that whenever it sticks, the kinetic energy is lost, right? It is only conserved in elastic collision. This is a perfectly inelastic scenario. So in the conserved, I should only have angular momentum, and in the non-conserved, yes, linear momentum and kinetic energy both are not conserved. So it has to be option A. Makes sense. Right, guys, that's all what we have for this video. I hope you liked this. It took a lot of effort to make this video for you guys. That's a really long video, but I hope you make the most out of it. If you like this, please like this, subscribe. If you have any doubts, post it down in the comment section. You can always download the worksheet from the link in the description, and if you need private tutoring, feel free to reach out. Thank you.